So, welcome.
Welcome to the GeoJSON webinar.
Yes, so we will tell you about GeoJSON today, and we will introduce ourselves first. So my name is Heiko Kernbach. I'm core developer at ArangoDB, and I'm working here since the launch. And the last couple of years, I created the front end, and now I'm more specializing myself into C++, especially geographical data and graph data.
Yeah, I'm Simon. I'm a core developer here. I do mostly C++. I work on the RocksDB engine, replication, the geo functionality, graphs, and AQL, and for example, the query profiler, and yeah, all kinds of things.
So let me tell you first something about the schedule for today. We will give a short introduction about multimodal and ArangoDB and how ArangoDB fits into multimodal. And then we will, of course, introduce all the new geo features and will describe something about the motivation. We will compare it, of course, with ArangoDB 3.4 and yeah, what's new. So we will also show you all new features. We will show you two different live demos. One demo is showing the Fox application we've created, and then we will also show you the user interface with basic queries and a bit more advanced queries where we combine geographical or geospatial data and graph data in one query. And the last topic will be the theory behind the Google S2 index library and how we included it into ArangoDB. So let's talk about multimodal databases. What is a multimodal database? So a multimodal database combines a document store, a graph database, and also key value store. And to query all of those types, there is one query language for all those three data models. And what is very important is that it is able to compete with specialized products and is quite easy to learn. So now about ArangoDB. ArangoDB is a document store, a key value store, and also a graph database. And it offers convenient queries which you can call via HTTP or REST or even, of course, AQL. And it gives you some guarantees, for example, using transactions or consistent guarantees inside there. And it's very easy to configure and set up. And it is distributed, so you can use it in a standalone environment or you can deploy it in a cluster environment, and it scales horizontally. And the best thing is it runs on all platforms, so you can use it on Linux, you can use it on Windows, and even on a Mac machine. So now a quick introduction into AQL and then Fox, because those two topics we will also need for this webinar. So a very brief, short introduction to this one. AQL is the Arango query language, and it is very complex, powerful, and with that you can write convenient queries with transaction semantics. You can do joins with that, you can query graphs, and AQL is of course completely independent of the driver which is used, so you can use it from ArangoJS, you can use it from Java, or I don't know, Go, and whatever you like. And it offers protection against injection by design. So quick introduction about what Fox is. Fox is a JavaScript framework which is included into ArangoDB. And with that, you can create microservices and, for example, extend your API by your user-defined microservices. And those are really directly running into your database, and they have access to the C++ core of the database engine. And with that, you can do schema validation, for example. You can do extended authorization. You can create their complex queries, which are custom-made. And you can, if you want, you can also create an UI to deliver some user interface. And if you want to learn more detail about ArangoDB and Fox itself, please go to the URL which is here included below. So now I will show you a very quick introduction to a Fox demo. And we created this one here. So this Fox demo is included inside the database. And for example, you can just deliver random restaurants and see them on a map. And those are GeoJSON points, which we will also explain in a few slides further. you can create or you can fetch random neighborhoods. And for example, if you have this neighborhood, you can just click there and you get directly all restaurants which are included here. And if you like, you can see the query, the executed query here, also the execution time, which is here 3 milliseconds, which is quite fast. And also how this works, basically, we will explain later. Also, I can show you the distance nearest query. I meant the distance between query, sorry, where you can see we want to display all restaurants which are between, so we have a starting point, the Statue of Liberty, and we want to display all restaurants which are basically included between those borders. So this first border is 25 kilometers far away from Statue of Liberty, and the outer border is 26 kilometers away. And with that query, we really fetch everything which is between those two lines. Last query I want to show you is the intersection query. Here we have a custom intersection area defined. That's basically just some area in New York City, and it is a polygon. And we want to go all our data sets, neighborhood data sets, which we also included in our database and we'll introduce also later. And then you can see that this query here, which is basically just iterating through all neighborhoods and intersecting them, delivers us all of those polygons which are intersecting our custom intersection area.
All right. Now let's talk about the new geo stuff. Right, then we showed you the Fox demo, which already is Fox combined with geo queries. We will have the link to that demo at the end. It's public on our GitHub repository. So right now, ArangoDB is a multimodal database. We support graphs, we support documents, and now we can combine this with context geo queries. And this is new in 3.4, right? So we released 3.4 last week. With a lot of other features like the optimized GeoRuxDB default storage engine. We have the load balancing support for Kubernetes and the cluster. There's the query profiling, the streaming cursors. There's a lot of new features in ArangoDB 3.4, and today we'll be mostly focusing on the GeoJSON stuff and the geospatial query capabilities. All right, so what's the motivation for this, right? So as we all know probably, geospatial data is everywhere now. So it's generated on your apps, well, your IoT devices. If you take a photo, it's geotagged. And social networks contain all kinds of geotagged data. You use it for transportation networks these days, in Uber, in navigation systems. And you want to be able to do real-time analysis on this data. You don't want to have to use specialized tools. You want to track it in your apps, immediately put it into your, connect it to your normal data, and use it to power your location-aware ads, do some business intelligence, all kinds of applications. And so the combination of this is something we want to support. We just want to support these use cases. We want to support as much of this as possible within our existing infrastructure and without using extra tools. And so what we added in 3.4 is specifically support for the GeoJSON, complex geometries, polygons, multi-polygons, line strings. In the old ArangoDB 3.3, only points were supported, queries that get you the points close to a certain target point, a maximum with like a maximum distance to that. We supported some simple polygon calculations, but nothing complicated. And the new ArangoDB supports intersections, containment queries, like is that object contained in a polygon? Does it intersect a polygon? Does it intersect a line string? And it's also all implemented via the Google S2 library, which is basically an industry standard for these kinds of things, and used in a lot of other databases. In ArangoDB, we use it for a little bit more than most other competitors, but we'll tell you about this later. Yeah.
Okay, let's continue with some basic information about GeoJSON. So GeoJSON is an open standard format, and it's founded by the Internet Engineering Task Force. And it's based on JSON. which fits perfectly to ArangoDB because we are already using JSON within ArangoDB and within our API. And of course, it supports points, line string, polygons, and also those multi-points, multi-line string, and so on. And it has a very basic definition, and it's just, as you can see below here in the picture, you have an object, a JSON object with two attributes, which are called type and coordinates. And for example, here we see line string, which have the coordinates, which has 3 coordinate pairs. As you see also in the picture, those are called, the first one 30, 10, the second one 10, 30, and then 40, 40. And just to explain what those values or those numbers are, you can see that the first one stands for the longitude value, for example, the 10 inside the 1030, and the second one, the 30, is standing for the latitude value. And I can tell you a very, very basic configuration setup we have also here included in our slide on the demo to show you how easy it is to just start with all that features. So for example, you see we have here a GeoJSON object, which is including a restaurant. And you see we have a location attribute here. And location is the position where our GeoJSON is included. And here it is included into a top level attribute, but we could also include it in a nested attribute, for example. So the position is not bound to the first level. And to configure the GeoIndex for that example, it's very easy. So you, for example, just use the Arango shell and select the restaurant collection where we have all our restaurant elements. And then you say ensure index, you say type geo, you say in which fields the GeoJSON is located in. And as you can see here, it is the location attribute. And then you say GeoJSON proof, just fire up that request and you have a running index on that specific location. So let me introduce you the new AQL features we have. So basically we have 2 different things. We have functions and we have constructors. So, and all of those functions are, you can use them with the index itself. And that's quite new because in our older version it was not possible. And you can use geodistance, you can use contains, you can use intersects to, for example, intersect one polygon with another. And you can also compare them or different types of GeoJSON with the equals function. And to help you a bit to improve or to easily write queries, so that you can basically easily can write queries, we also have constructor functions, as you can see on the right side. And there we have GeoPoints, GeoLine string, multi-line string, polygon, and multi-polygon, and they will help you to set the GeoJSON infra objects setup. So one very basic example, we want to create a geo point, and then you only say in AQL geo_point, put in those 2 values, those longitude and latitude values, fire that request, and then you will have a valid GeoJSON object. The same thing will also work for polygons. Just say geo_polygon, include your longitude latitude pairs inside that array, and then you will also get a valid GeoJSON polygon. Okay, let me show you a very basic example of the geo_equals function. We define a geopoint A, which is 1.0 and 2.0, and a geopoint B, which is 3.0 and 4.0. And as you can see, it's very basic. So we now compare A, and you see that this is true. And then if we compare A and B, you see that this is false, or this will return false. And of course, you can use any GeoJSON types there. So you are not bound to use geopoint, but you could also compare the equality of 2 polygons inside this function. Then we have a very basic geodistance example. And it's, so imagine we have the Statue of Liberty in our center, and we want to return all restaurants within the maximum distance of 30 kilometers. So in our query, we define our Statue of Liberty, and this is the geopoint of 1 coordinate pair. And then we iterate through all restaurants that you can see in the second line. So we iterate with for restaurant in restaurants. And then we say, oh, we want to apply a filter. So we will say filter, geodistance. Then we say, where's our starting point? And this is the Statue of Liberty. And with which points we want to compare. And here we want to compare with the location of all of our restaurants. And the GeoJSON attribute or the value is stored inside the attribute of restaurant.location. So we need to apply this value here and say it is smaller or equal than 30,000. And then we will just say return this location, and this will deliver us all restaurants which are in the reach of a maximum distance of 30 kilometers. Next example. It is very similar to the previous one, but as you can see, we now have a second filter applied. We don't only have the smaller equal 30,000 filter, but now we also added a bigger or equal 25,000 filter. And as I showed you previously in the Fox application, we have those two circles here in the image, and we exactly get those restaurants which are included between those two borders. And this is basically what which we used here. So we used a distance between query here with the same functionality, but two filters included. So next geodistance query would be, for example, we want to return the 100 nearest restaurants sorted by their distance, also starting from the Statue of Liberty. Here we also iterate through all the restaurants, define our starting position, but now we say sort, also apply our new function geodistance, use the center, so the Statue of the Liberty, put in our restaurant location, and say, please sort it ascending and limit it to 100. And this will return us the 100 nearest restaurants from beginning from the Statue of Liberty position. So now a basic geo-contains example. We want to show all restaurants which are contained inside the neighborhood Chinatown. So we have now a new collection called neighborhoods, and in the neighborhoods collection we have lots of neighborhoods. So first we want to find the one which is called Chinatown. So we say filter n.name equals Chinatown and put it into the variable Chinatown. Then we iterate through all the restaurants and we say filter geocontains Chinatown.geometry, because that is the location of our GeoJSON inside the Chinatown neighborhood, and say as a second attribute restaurant.location to compare whether the restaurant is located inside the neighborhood or not, and then we will just return it. And this will deliver us all the restaurants which are included inside the polygon of the Chinatown geometry. And also now the GeoIntersection example, which I also showed you in the Fox application just a few minutes ago. We have here a custom intersection area, the sum area New York City polygon, and we now want to see which neighborhoods are intersecting with that user-defined custom intersection area. So we again iterate through all the neighborhoods, and now we say filter GeoIntersect, define again our sum area in New York City, then define the location of the neighborhood geometry, which is included in the iterator n.geometry, and just return it. And then you can see all those green polygons on the right side are returned from that specific query. And during the development, we realized that its geometrical calculations are working pretty nice and fast, but something was missing. And the something was we wanted to visualize the data, because geographical or geospatial data is perfect for drawing them on a map. So we included a map inside our AQL editor and improved it. And so starting from the release 3.4, you are able to also display all types of GeoJSON inside your user interface by using the AQL editor. Okay,
to skip something.
Yeah.
Anyway, so I think now we're going to show you like some of the queries that we just saw live in our web UI, and then we're going to have a quick look at the web editor that you can see. Sort of very simple example, right? That we did initially. It's a very simple example, right? We have the one point in GeoJSON rendered on a map. You can see the index itself here. If the JSON data itself is just JSON, And ArangoDB is no special type at all. You can just edit it or transform it in AQL like any other document you get from ArangoDB, any JSON document. You can also use it in any driver. The drivers are not only any special support for this, they can just use the normal object. So anyway, next simple example was the polygon, right? This just returns the geopolygon. It works exactly the same. You get the type, GeoJSON type, coordinates, and that's it. That's really all it is. And sorry. Anyway, the next thing is, for example, the equality. I think we don't really need to show that. Oh yeah, the distance query, right? So this is the first query that should actually use all the indexing, right? So here we see the Statue of Liberty in the middle, right? And then all the restaurants that are close to it in New York, not in New Jersey, because the data set only includes data in New York. And of course, we only fetch 1,000 elements for the web UI. So, and the JSON contains the same stuff, right? You can look at it in the familiar table setup. It's all the same. So now, just to verify, we can use the explain output here to see, all right, this actually uses an index node here. We can see the geoindex optimizer rule was applied. We see the range was defined as this geodistance query. Don't really have selectivity or anything else here, but we can see basically we just need a calculation node to do the projection to the restaurant. And we do that here because the web UI will just look at the result documents with a pretty simple rule and to try to determine whether that's GeoJSON. If it is GeoJSON, it will try to show it on the map. And so if we just return a restaurant with the restaurant itself, then we will not get that nice visualization. But it still works, of course. Okay, what else is interesting? Maybe the intersection query, the containment query. It's actually difficult. Yeah, but this was the Chinatown version. Yeah, really simple stuff. Just our restaurants in Chinatown. Anyway, the next thing. So now I'm going to show you some combined zero queries, right? We talked about multimodal in the beginning, and it's really all about the multimodal approach where you can combine graph queries or complex joins or whatever, and then do a GeoQuery with that data. So we got a simple graph here, right? If you had the original data just contained neighborhoods and people, or neighborhoods and restaurants. And now we add people to that, and we add edge collections to that. So now we have people that visited restaurants, we have people that know each other in like a simple social network. We have neighborhoods and people that live in neighborhoods, all connected via simple edge collections in ArangoDB. And this is all generated data. People are not real. That's not actual data. It's available in our example data set repository. And it's all randomly generated, so don't expect it. It's all pretty simple. So, oh yeah, let's first show you the query that I have here. So the first example that I wanted to do here with ArangoDB is I'm in a certain area, let's say Long Island City in New York. It's a neighborhood. I'm Janet Liebrecht, that's my name, and I want to get all the restaurants that friends of friends of mine visited already in Long Island City. And that's really easy in ArangoDB, right? You can do a simple graph query with traversal depth 2 in the nose collection, and then check that for cross-reference that with all the restaurants that are in the neighborhood. And that's it really, right? Simple 8-line query. Yeah, let's show that in the web editor. Let's close all of these.
Just really click on
remove. Anyway, that's the containment query here. Right, and these are all the restaurants around in Long Island City. We have Janet Liebrecht. Like in an actual application, you would probably already know the actual ID of the person that you want to start off from. In this example, for the illustrative part, I used name and first name and last name to match the person first, but you probably wouldn't need that for loop. Yeah, and then we get our restaurants. We get then just all restaurants that are in Long Island City. And then do a traversal from the restaurant to the friend, right? So that's really all it is. Yeah. And if you look at the explain output here, we really just don't see that much, right? We have we use the index node here. It's all optimized, and it's really easy. Anyway, then the next example that I had was show me neighborhoods where friends of mine are living, like only neighborhoods where actually friends of mine live. And that's similar, right? We have the we look for Janet, we do a traversal with depth2 from where people that live there I know, and then we look from that, we look inside the lives collection, and then we make a distance calculation to make sure that we only get neighborhoods that are close by. And just for reference, we have the following collection, right? We have the lives visitor collection that is just, no, we actually don't need that. We have the lives collection from people to neighborhoods, right? Where it's just one edge from every person to one neighborhood. Then we have nodes collection from a random person to another random person. And that's really almost all we need here. And so let's try this query. And you see it runs in 300 milliseconds. We get all the neighborhoods for people that I know live. And it's also just JSON in the end. So now we can see one thing that I wanted to get what's the query profile, right? So when we look at this here, this is it's not quite fast. Like 300 milliseconds is not super fast. And we see that in the new query profile, you can see the number of items that every stage in the query went through. And we see we get 260 results, and almost all the time that are spent in like this distance calculation. And if you look at it, it makes sense because the distance calculation is not optimized by an index here. So, and the distance calculation is expensive because these are polygons, right? We have to parse these polygons, calculate their shape, then do the distance calculation, and it almost takes more than a millisecond per item. And this center that we actually want to calculate this against is, of course, Central Park, I think. But anyway, like the way we can improve this is like we can turn this query around, right? We can just first get all the neighborhoods around us and then try to match from neighborhoods to friends of mine. So I made a quick query here. We just match for Janet first here. We then look inside all the neighborhoods that are around me in 5 kilometers distance, and then check in the graph query, in the lives collection, and then in the nodes collection, if there are people if there are basically paths from the neighborhood to me, right? And then check whether there's at least one path here in that subquery. And we should see that this is matching. Not quite, but 2 milliseconds about. It's 1/3 faster at least. Anyway, and yeah, that's the query profiling. Yeah, that was a quick live demo. The link to the Fox demo earlier is here. It's in the ArangoDB Fox repository.
Yeah, also the dataset of restaurants and neighborhoods are included inside this names repository.
Yeah.
Yeah, we're just missing is our random generated edge.
Yeah, we might upload that later. Okay, so now let's get to how it actually works. Like the GeoIndex itself, right? It doesn't actually use in Quadtree right now, but let's start off with that for just to get the idea, basically. And let's preface this with there's a blog post from myself. There are multiple blog posts actually, where this is also explains where all these images are. And I'm going to link to these later. But let's first start off like assume you have like the Earth, or you have a part of the world somewhere on the globe, right? And you got this quadrant, and then you can subdivide all the areas in this plane and put them inside this quadrant. So let's say you have this point A, and this corresponds to like a node in this tree. So 1 is in the entire thing, 2 is just the upper left quadrant, and then 2 is also subdivided into 4 quadrants, and A is just contained in the last one. And this works, right? Like you can, if you want to index something, you can put all the points in their proper nodes or buckets, and if you want to search for something in an area, you just look inside the corresponding buckets and you'll find it again. But this is not quite ideal because these trees, they don't work so well for if you want to store them on disk, and it's all in memory. It's not cache efficient. So what you do next is you can figure out that you actually don't need quadtrees at all, right? You can just say the height of you have a fixed amount of detail. The quadtree has like an unlimited amount of detail because you can subdivide things as long as you want. But if you say, all right, this has a fixed amount of detail, and you don't need it at all. You just say, all right, every node in my tree corresponds to some value as a fixed string that you can call geohash. And if you put that geohash in the sorted list, you can just look up in that list, and every range in that list corresponds to an area here. So for example, to take the same example, here we have the point A on the left, and then we're going to take point P on the upper right. And in the quadtree, it would be probably around here somewhere in the tree or something. But in P, you actually just assign it a string. So you look in the first level, the entire quadrant, it's on latitude 0, this upper half, and then longitude 1 in the right half. So you got this quadrant. And then on the second depth, latitude 2 and longitude 2, it's also on 0 and 1. So now you have the string, and you can put it in an index. And if you want to index the entire quadrant, then you just put this in, and this is basically a prefix. Everything that's more detailed in here has the same prefix. So you can, if you want to index a circle approximately, just rasterize it essentially. You just say, all right, I got this first quadrant here, and I put a string in my index. I just put the corresponding geohash for this, the string essentially, and this quadrant, and this quadrant, and this quadrant, and this quadrant. And if I want to look for any object in that area, I will just scan over the ranges that these might be in, which is really easy if you can solve them, right? The problem with this is that this approach isn't quite ideal because these are not necessarily adjacent. Like the problem is here we went from this to there, right? Like the way we index this is not ideal because we have to switch around. Like we have to jump from here to this one, and this one, and this one are not connected. So if you sort it by the string, you can't really have your areas are not connected ideally. This might sound complicated, but the end result is that you want to change the way you index these things, or you map these tiles to numbers essentially, or to geohashes. So what you do is you use the special Hilbert curve, which basically starts off with a new shape and can be extended for every detail level. And the nice property of this is that every increasing number, every increasing geohash is adjacent in your space, like on the Earth. So it's much better to rasterize actual shapes. Anyway, now we're going to look at some examples of this because it's much easier to understand then. So this space, what we basically do is we have values in our index, and they are increasing along this line, and then we map this back onto the globe at some point at whatever detail we want. And this is really nice for indexing because you can just scan in your index and you find adjacent areas and you find points or polygons, whatever you have. And so, for example, if you want to index a square, you just rasterize it into these ranges of things, which are just short strings, and we put that in the index and we can use it to index stuff. Anyway, it's all in much more detail in my article. If you have any questions about that, can read up more details there. I hope that gives you an idea of how it works. And yeah, I think we're already almost at the end here. Yeah, the article is linked there. The two example apps are also linked there. We didn't make them. They're from Sidewalk Labs. That's I think an Alphabet company. And yeah, join our Slack channel, the geospatial Slack channel.
If you have any questions, feel free to ask there.
Yeah.
So, or I don't know, have specific wishes or improvements, or I don't know, want to just say anything about geospatial, just feel free to join there and ask us questions. We would be very happy. And also, you can see a GeoJSON tutorial linked here, which is also maybe just summarizing this webinar. So also feel free to read this one. And if you have further questions, everything should be documented in our documentation, which you can find under docs.arangodb.com.
All right, that's it.
So I think basically that's it.